Hello, everyone. My name is Krishnan Raghavan, and I am going to present on model parallelization in deep neural networks. This paper was written in conjunction with Shweta, who worked with me on a summer project with respect to this paper under the guidance of Jagannathan and Samaranayake in Missouri University of Science and Technology. To start with, we're going to consider a standard neural network with D layers. Each layer is represented by FT, which represents the nonlinearity at that layer, and WD, which represents the weight at that layer. Now, I'm considering a supervised learning setup in which there is a learning phase and a testing phase, and the data is given to us as a tuple of X and Y. We will consider a simple cost function, which is an L2 norm cost function, which will basically be given as an error square. Error is defined as target minus output of the neural network. The optimization problem that we intend to solve requires us to minimize the cost function with respect to the weight of the neural network, which is collectively denoted as theta. This optimization problem is consistently solved in the literature with different optimizers such as Adam, EDA grad, EDA delta. The common theme in all of these optimization approaches is the fact that they are based on backpropagation algorithm. And there are many drawbacks to these algorithms. We'll start with drawbacks considering backpropagation. To think about backpropagation, we will define the update weight update as a derivative of the cost function with respect to weight at that layer. When you describe the derivative of the cost function with respect to weight at that layer, you by chain rule, you will split it across many partial derivatives in which all the partial derivatives highlighted in blue are of the activation function. When the value of activation function, there are two components to a partial derivative, the magnitude of the partial derivative and the direction into the sign of the partial derivative. When the value of the activation function is less than 1, that is between 0 and 1 or negative 1 to 1, you will get a phenomenon in which many small values between 0 and 1 will get multiplied. Number of layer keeps on increasing, this multiplicative value starts pushing 0. Similarly, each partial derivatives introduce a different direction of learning, which leads to a non-convex optimization, which is really hard to solve. On the other hand, in spite of challenges with backpropagation, on the other hand, there are many challenges with respect to parallelization as well. Standard approach to parallelization is as follows. You have multiple copies of neural network that needs to be maintained. These copies are then spread across different nodes on the neural network. The data is also split across different nodes, and then each neural network in this node is learned based on different types of data, different parts of the data given to them. This setup leads to recognizing an elephant problem in which each part of the element is recognized by a different neural network, and none of them, when this data is merged together, none of them can really give a full picture of the data, which is the standard issues with such approaches. Now, a core issue which leads to these problems with optimization and deep neural networks is the compositional structure of neural network. By compositional structure, we mean the idea that one layer is given as an input to the next layer in a neural network setup. This compositional structure of neural network, if broken, can be a solution to this problem in which you can allow model parallelization as well as data parallelization without getting into the problems due to a non-convex optimization. And that is the main contribution of this work, and that is what I'm going to talk about today. So, to talk about our distributed learning methodology, we'll take a simple three-layer neural network where there are three weight parameters, W3, W2, and W1, and three activation function, F3, F2, and F1. To start our methodology is inherently dependent on introducing additional variables which take place of each layer in the neural network, such that the connection between one layer to another layer can be broken, and the connection for the input to every layer is this additional variable instead of the previous layer. To illustrate this, let's start by introducing an additional variable Z3 in the place of the top layer of the neural network, that is the third layer of the neural network. With this introduction of first variable, your y hat, which is the output of the neural network, now becomes dependent on Z3 instead of depending on all the other layers, such that Z3 is constrained to be equivalent to the previous layers. Now, this neural network, this is not a neural network unless Z3 is equivalent to Z3 represents all the data that is going to come from the previous layer. Therefore, Z3 has to be constrained to be equal to all the previous layers of the neural network, which is layer 2 and layer 3, 2, and 1. Similarly, let's introduce another additional variable, which is Z2, such that now the output of Z3, output Z3 is depends on Z2, and Z2 is constrained to depend to be equivalent to the first layer and the second layer in the neural network. By introducing these two additional variables, our optimization problem has changed now. The change in the optimization problem is as follows. In standard case, our optimization problem, the cost function was written as y minus y hat. By introducing these additional variables, we have introduced the constraints because of additional variables, which is Z3 and Z2, each of which is constrained to be equal to the previous layers. Now note that these constraints are implicitly present in a standard neural network, and we do not think of them as constraints. We just set Z3 equal to the previous layer of the neural network, and there is that. What we are proposing in this work is that instead of setting Z3 equal to the previous layer, we will update Z3 or rather learn Z3 such that we can mimic the output of the previous layers. By to learn Z3 as another variable, instead of just setting these constraints equal, we will define a penalty-based cost function in which J, the y hat, introduces two additional components. Each component is a penalty function that satisfies the constraint on Z3 and Z2 independently. If you do this kind of an introduction of an additional variable for every layer in the neural network, what you obtain is for each layer, your input is Z. Z goes through the activation function F. This activation function then gets multiplied by the weight at that layer, that layer, and that is your output. That is your output to the output of that layer. Using that output of that layer, you will constrain the input to the next layer to be equal to the output of the previous layer, and this type of behavior will lead to many additional variables. So by constraint, we mean that each additional variable can be introduced an observer that is required to estimate the output at the previous layer. So the main contribution of the main idea in this work is basically that instead of directly learning the neural network weights, we learn Z variables first, such that Z's can achieve the constraints that have been imposed on it as part of the optimization problem. After Z variables are learned, we update the weight parameters. However, this introduction of Z variables introduce additional parameters, hyperparameters that needs to be tuned, such as the penalty function parameters and sparsity parameters, and as follows, because that will lead to computational improvements. But these are too many parameters to set by hand. So what we will do is we will formulate this as a two-player optimization problem where the cost function is maximized with respect to the penalty parameter and minimized with respect to the parameters of the neural network. When the Z constraints are introduced, this final cost constraint optimization problem is written as follows. With respect to this new optimization problem, theoretically, we can show that this new optimization problem is equivalent to the old optimization problem. We can also show that the saddle point exists, and a main result of our paper is that each of these optimization problems independently is convex, and this can be really easily thought about because each of these optimization problem only depends on the weight at that layer and Z at that layer, and provided the activation function is chosen properly, this optimization problem is convex with respect to the parameters at that layer. Overall, as I mentioned before, the algorithm basically involves two loops. In the first loop, you have to update all the Z's so that the Z's approach the constraint that they have been imposed on. And then once this loop is finished, the outer loop gets updated. The important point to note is that no communication is happening between each layer of this neural network. Each of these layers can be set up on different nodes in a highly parallel supercomputer, and data and so this which will provide us with data and model parallelization, which was the aim of our work in overall. In result, when we use Stannard's hyperbolic activation function and vary the number of layers, we see how well the rate of convergence and the accuracy values, we observe that with respect to the additional variables, we observe faster convergence. Observe that the red plot reaches a very low cost function much faster than the black one. Similarly, we observe that as the number of layers increase, better accuracies are achieved for the case when z variables are introduced, corresponding to case when z variables are not present. Therefore, the accuracy with the number of layers for the z is better, which is also observed with respect to different data sets such as Arsine, Dexter, Gizet, Madelon, and MLIS. Finally, we conclude that for a layer-wise optimization problem that we proposed, a layer-wise optimization approach that we proposed has several advantages. This highly scalable neural network approach performs several advantages. The non-convex optimization problem has been split into multiple optimization problems. Each of them are probably convex. The vanishing gradient problem doesn't exist anymore because the gradient at each optimization problem is only a function of one layer. Therefore, the number of layers do not impact the learning scheme. But the big drawback of this approach is the fact that additional computational complexity is introduced because of these new variables, and parallelization techniques can reduce the impact of these computational complexities. One such parallelization technique was presented in this paper. However, because of lack of time, we are not able to discuss this.